Hello world. In today's video, we are going to look at Newton's first law of motion. So this is one of the Newton's laws. So Newton came up with um, a laws which describe the motion of objects. He describes the motion of objects which are at rest, objects which are moving with constant velocity, and even objects which are accelerating. But today we are only going to focus on the first law of motion. According to the examination guideline of grade 11 2015, Newton's first law of motion states that an object will remain in its state of rest or motion at constant velocity unless a non-zero resultant force acts on it. If you were to interpret this in simple layman terms, what it means is an object will continue to maintain its constant velocity. So that constant velocity could be a zero velocity or a non-zero velocity. This will happen if and only if the net force acting on the object is zero. So remember we spoke about these objects which were at rest, which or objects which were moving at constant velocity. We said that such objects were in a state of equilibrium. And we said if an object is in equilibrium, it means that the opposing forces acting on this object are balanced. And most importantly, we said that the net force acting on the object will be equals to 0 Newton. So this is Newton's first law of motion in words. This will be Newton's first law of motion in mathematical form. Remember that mathematics is the language of physics. So for an object which is at rest, net force acting on the object will be equals to 0. If the object moves with constant velocity, the same thing is applicable. But remember when we were in grade 10, we spoke a lot about objects that were at rest or objects that were moving with a constant velocity. And when we looked at this chapter of motion in one dimension in grade 10, we went into a great detail into plotting the graphs for these objects. I'm going to start with objects which are at rest. So at rest. So for an object which is at rest, we said that this object is not moving. And if the object is not moving, what will be the speed? What will be the velocity? The velocity will just simply be 0 because it's not moving. Okay. And if it's not moving, most importantly, it means that the position of the object, position is not changing. So the object is not changing where it is located at a specific point in time. So using these statements, I can plot a couple of graphs. I'm gonna start with the position time graph. Position, I'm gonna represent it by x in meters as a function of time in seconds. So this is position versus time graph. Because it's not moving, then the position remains the same. So if this object was standing at a position of 5 meters from the origin, then that's where it's going to be. After a second, it will still be there. One more second later, it's still there. At a later stage, it's still at the same position. On the y-axis, we plotted the position. And we can also plot the velocity time graph, velocity versus time graph. It's going to look something like this. Remember to always label your axes. Is it function of time in seconds? Gonna draw this in blue so that it's visible. We said for an object that is at rest, which is not moving, the velocity is 0. So for as long as it's standing, the velocity is 0. So if you look at this graph, it's on the x-axis, and this is because time waits for no man. 1 second later, velocity is 0. 2 seconds later, still 0, so on and so forth. Time does not wait for no man. So let us say when we started measuring, this object was somewhere there, 5 meters from the origin. That's when we start measuring, and then the time goes on. Remember, time does not stop moving. So because time moves, it's just going to drag that into a line which is parallel to the x-axis. The velocity when we started measuring, it was 0, but because time is the one which is moving, it drags this along the x-axis. And we can also go as far as plotting the acceleration versus time graph. A versus time graph. So remember what acceleration is. By definition, acceleration is the rate of change in velocity. So if I put that in mathematical form, it looks something like this. The rate of change in velocity. Because the velocity is 0 throughout. Remember to calculate change in velocity, or in general, to calculate the change in any physical quantity. The change in any physical quantity, x represents any physical quantity. It will be the final of the physical quantity minus the initial. So it means when I talk about the change in temperature, that will be the final temperature minus the initial temperature. And because over here I'm talking about the change in velocity, can you guess how we calculate change in velocity? Just as a reminder from grade 10 work. To calculate change in velocity, you guessed it right, that will be the final velocity minus the initial velocity. But because the velocity was 0 throughout, it means final velocity is 0, initial is 0, change in time is non-zero. So this will be 0 over change in time. Remember that 0 divided by any number will always be equals to 0. So most importantly, for an object that is moving with for an object that is at rest, I'm going to add to this little summary of mine. For an object that is at rest, velocity is 0, acceleration is also 0 in units of meters per square second. So if I were to plot the graph of acceleration, okay, I'm doing this, writing all these units so that you also do it all the time. The acceleration, when we start at 0, because time is moving, it's going to drag this along the x-axis, and that will be your graph. This is grade 10 work. And we can make an extension here into grade 11 work. Remember, we have just said that for an object that is at rest, we have said that F net is equals to 0. So we can plot the graph of net force as a function of time. So F net in Newton as a function of time in seconds. You can try to predict how the graph would look like. So that's how the graph is going to look like. Yippee! Okay. So now I want us to talk a little bit about an object that is moving with a constant velocity. And I'm going to try to erase this. When we say an object is moving with a constant velocity, please note that the object is moving, unlike the one that we've been talking about. It means that the velocity of the object is not changing. So constant velocity. Velocity is not changing. And what can we say about the acceleration? The next note here will be about the acceleration. Remember to calculate acceleration. Acceleration is equals to, as we have just said a couple of seconds ago, we said that acceleration is the rate of change in velocity. But what we are saying is the velocity is not changing. If velocity is not changing, it means that the change in velocity will be 0. So this will be 0 divided by delta t. It will also give us 0. So for an object that is moving with a constant velocity, the acceleration of that object will be 0 meters per second. So if we go back to these graphs, I'm only going to erase the one for position versus time, as well as velocity versus time, because those are the ones which are going to look a little bit different. But the rest of the graphs, the last two graphs, are exactly the same. If an object is moving with a constant velocity, acceleration is 0, the acceleration time graph will be that one over there. This will be the acceleration versus time graph. If the object moves with constant velocity, we have also said that the net force will be close to 0 Newton. If we plot the graph of net force versus time, that will be that graph over there. But let us plot the velocity time graph. Velocity versus time. Velocity in units of meters per second. So we've said that if velocity is constant, it means it's not changing. So let us say that the velocity was 2 meters per second in the positive direction. That value there is 2. So that value of the velocity is not going to change. Only time is changing. Time is moving. So what it will do is it will just drag that point in that direction. So if this is 1 second, this is 2 seconds, 3 seconds. If we try to read off the value of the velocity at t equals to 1 second, the velocity was still 2. At time equals to 2 seconds, velocity was still 2. At a later stage, it was still 2, to show that the velocity is not changing. So the last one being the position versus time graph versus time. I'm gonna draw my axes. Time in seconds, position in meters. So before we draw this graph, I want us to understand what constant velocity means for the position. Remember how we calculate the velocity of an object. To calculate the velocity of an object, provided the object moves with constant velocity, we said we can use the formula v equals to, and this is actually the definition of a velocity. When we define velocity, we define it as the rate of change in position. And the position of the object is indeed changing because the object is moving from one position to another. So let us say that the velocity that we are talking about, we are told that it is 2 meters per second. So what this means in words, it means 2 meters per second. Remember what we put on the numerator, that was the change in position. What this means is the position changes by 2 meters for every second that passes. So it means that the position is changing with the same interval for every second that passes. So if I were to tabulate this, let us say that the object starts at the origin. Which part do I erase? I'm going to erase this part over here. I hope you already have that summary there. Okay, I wish I had a quicker way of cleaning up my screen. Okay, so we said this means 2 meters per second. So it means that every second that passes, the position changes by 2 meters. So let us say this object is initially standing at the origin. This is time. So at the origin, the reference point, the 0 point, at time t equals to 0, and the time changes with intervals of 1 second. 1 second later, 1 second later is 2, and then 1 second later, 1 second later. What we are saying with this is the position changes by 2 meters for every second that passes. If it was initially at the origin, the position will change by 2. What will be the new position? The new position will be 2 meters. It will be at a point 2 meters from the origin. A second later, 1 second later, the position is going to change again by 2 meters. It was at 2, now it changes by 2 meters. It is now at a position of 4 meters. So this will be 4 meters. If you add another 2 meters, that will be 6, that will be 8, that will be 10. So if you look at these points, you can use them to actually plot a graph. The point 0, 0 is somewhere there. The point, I'm going to write 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And then the other coordinate, the other coordinate, the other coordinate, and then the other coordinate. And you can join them with a line. Okay, and that will be our graph over there. With straight line graphs, remember that they have a gradient. So over here, I want us to determine the gradient. So from mathematics, gradient m, let me just write it in words because the m's in physical sciences actually mean a lot of things. So I'm trying to avoid confusion. I'm going to say gradient. Gradient from mathematics, in maths they represented by small m. Gradient is equals to the change in y over the change in x. But I want to bring this home. I want us to bring it to physics. What did we plot along the y-axis? We plotted position. The y-axis are as the vertical line. On the y-axis we plotted x. So instead of writing y, I'm going to write x. This is change in x divided by change in x. So this x here on that formula refers to the x-axis. So what did we plot along the x-axis? We plotted time. So instead of writing x, I'm going to put the suitable physical quantity. So the gradient is change in x over change in t. But we have seen that before. This is the rate of change in position. And what is that? That is velocity. It means that the gradient of this graph is equals to the velocity. And it makes sense with straight line graphs. The gradient of a straight line graph is constant. What is the gradient? Is the velocity. It means that the velocity is constant. And when we drew the graph, we found that the velocity was indeed constant. So that is the graphical part of it. So if you're given position time graph, you can use it to calculate the velocity of the object. And this is how the graphs they differ. So we've been talking about Newton's first law of motion, which led us to all of that. And we said with Newton's first law, we are describing objects which are at rest or moving with a constant velocity. The net force acting on those objects will be 0. And in the previous video where we spoke about equilibrium, we have seen that for this statement to be true, the sum of the forces along the x direction needs to be equals to 0 Newton, And the sum of the forces along the y direction also needs to be equal to 0 Newton. Remember, F net means sum of forces. And I want us to apply this Newton's first law of motion to solve for problems. We only use this provided it's a Newton's first law problem. How do we know it's a Newton's first law problem? The object is either at rest or it's moving with a constant velocity. Never assume that an object is at rest. Never assume that object is moving with constant velocity unless the statement says so. So let us look at this example. It says a force F of unknown magnitude. So there's the force. We don't know the size of this force is applied on an object, causing it to move to the left with a constant velocity. So constant velocity, immediately we should be thinking acceleration is 0. We should also be thinking F net is equals to 0. We should be thinking that the object is in equilibrium. I know I'm abusing the equilibrium word here. It's the forces in equilibrium, but yeah, don't mind my vocab for now. Okay. So because of that tiny detail, we have come up with this little bit of a summary there. And it's very important to underline important things from the statement. And then it says the coefficient of static friction and coefficient of kinetic friction are 0,5 and 0,2 respectively, in that order that was given. It means coefficient of static friction is 0,5 and coefficient of kinetic friction, because they mentioned it last, it means that is the corresponding coefficient. Even if they didn't tell you which one is which, remember what I said the other day. I said the coefficient of static friction is always greater than the coefficient of kinetic friction, so the smaller one is mu k. Okay, so this is the information that they have given to us. So we need to decide on which one we are going to be using here. And remember, do not assume the surface is frictionless unless they say so. So they did not say anything here about the surface being frictionless. But for the mere fact that they give us the coefficient, it means that the surface is rough. It's not frictionless. There's friction there. Okay. So we have friction. Now we need to decide which one. Because they said that the object was moving, it moves. It means we have kinetic frictional force. Okay, how do we calculate it? That was mu k multiplied by normal. This formula is always on your data sheet. The first question says, draw a free body diagram showing all the forces acting on the block. Whether you like it or not, you need the free body diagram to solve the problem. Whether they ask for it or they don't ask for it, you need the free body diagram. Okay, let me put my free body diagram somewhere here, up here, so that I can keep on referring to it. So remember I said before you draw your free body diagram, draw the set of axes. Perpendicular to the surface y-axis, parallel to the surface x-axis, and then I can include my forces. Pointing perpendicular to the surface away from it, that is the normal force, and I hope you still remember how to define normal force. Always pointing vertically downwards, that is my weight. Force applied, you don't ever need to worry about drawing the applied force. That one, you draw it as it appears on the sketch. So that one will be the force applied. And lastly, kinetic friction. Where is the object going? Towards the left. Kinetic friction opposes the motion of the object, so it will be opposite to the direction of motion. This will be Fk. Okay. And then the other question says classify the question as the forces as being contact or non-contact. Okay. This one, let us start with the normal force. We require contact with the surface, so this is contact force. Fk, we need contact with the rough surface. This is a contact force. Weight, we don't need contact with the earth for us to have weight, so this is a non-contact. I'm going to use green. And then we have applied force. Whatever that is applying this force must be in contact with the object. So the ones which are in blue, these are the contact forces. The one in green, that is a non-contact force. And the other question says calculate the normal force acting on the block. Yes. How do we calculate it? Remember, we have the most powerful tool. We have Newton's first law. F net equals to 0 Newton. And we said that this means that F net along the x is equals to 0. F net along the y is equals to 0. So if we are asked to calculate a force, it does not matter which force. So we can start looking at these equations, these two equations over here. If we are asked to calculate kinetic frictional force, it goes two ways. To calculate kinetic frictional force, you can either make use of this equation, or if you have too many unknowns, you can still come back here. So to identify which one you use, sum of forces along the x direction or sum of forces along the y direction, you need to look at the force that they're talking about and identify the direction in which it is along. If we look at the normal force, that's what we're trying to calculate. It's along the y direction. So we need to sum forces along the y direction to find the normal force. And in general, you'll realize that to calculate the normal force, you need to sum forces along the y direction. Sum of forces along the y direction equals to 0. What do we have along the y direction? I have the normal force. I also have the weight, which are collinear. I just need to pick a positive direction. I'm going to pick down as positive for interest sake. So it means which one is pointing down? The weight. I have weight in the positive direction, plus the normal force in the negative direction, minus, and the minus is for direction. If I sum them, I'll get a value of 0. But whoa, how do we calculate the weight? Remember we said the weight was equals to the mass multiplied by gravitational acceleration. I didn't give the mass of the block. Let's just assume it's 5 kilogram block. So the weight will be equals to 5 multiplied by 9,8. If I punch that on calculator, I find that the weight of the block will be 49 newtons. Okay, then I can sub n. I have 49 minus n equals to 0. If I move n to the other side, I have that n is equals to 49 newtons. This is the magnitude of the normal force. I already know the direction. I already subbed in the direction. Okay, so from the free body diagram, I can indicate that the normal force is 49 newton, but that's fine. Okay. And then the last question is calculate the magnitude of the applied force. In which axis do we find the force applied? We find the force applied along the x direction. So we need to sum forces along the x direction. Sum of forces along the x direction should give me a value of 0 Newton. What do I have along the x direction? I have force applied in Fk, and it's more advisable to pick the direction of motion as positive. So I'm going to take direction of motion as positive, meaning left is positive. I have force applied plus minus for direction of the Fk because it's pointing right. If I sum those, I should get a value of 0. And I have force applied minus Fk equals to 0 Newton. Do I know Fk? No, I don't. But can I calculate it? Let me see. Do I have mu k? Yes, I do. Do I have the normal? Yes, I do. Then I can calculate the kinetic frictional force. If you like, you can do this on a different space. This will be equals to mu k, which is 0,2 multiplied by 49. This should give me a value of 0. So I'm going to do the calculation on the side so that you can clearly see what I am doing over here. So I'm saying that Fk is equals to mu k multiplied by the normal. Mu k is 0,2. Normal we just calculated. That is 49. If you punch on a calculator, you're going to get a value of 9,8 Newton. So I'm going to sub that value in there. Minus 9,8. If I transpose, I have that applied force is equals to 9,8 Newton. And yippee, we are happy and we are done. Okay, so in the next video, we are gonna look at more problems where we are going to be applying Newton's first law. So I think what I'm gonna do is in the next 3 videos, we are we are going to be solving problems using Newton's first law of motion. And in the last video, I'm going to try to bring a problem where we incorporate 2 different objects. Because if you look here, I only had one object, which was a block. That's it from me for today. Until we meet again, bye and thank you.